I have two metals here that look very similar, but they're actually quite different. It turns out that one of them is a crystalline metal and the other one is amorphous. But before we learn more about that, let's do an experiment. I'm going to give you each a ball bearing, and I want you to hold it at the top of the tube, and on the count of 3, we're going to drop it. 1, 2, 3. Wow, that one bounces a lot. It turns out that these two metals are quite a bit different. This one's made out of stainless steel, which is crystalline, and it's like a lot of the metallic materials that are around us in the world every day. But this is a different kind of metal. It's called an amorphous metal, and this particular alloy is called vitrolloy. It actually has 5 different kinds of atoms in it. The stainless steel also has different atoms in it, but because of the arrangement, this one being crystalline and this one being amorphous, they behave very differently. So what can you notice about the surface of these two metals? We've bounced a lot of balls on these two plates, so what do you notice when you take a good look at them? You're right, there's a lot of dents on it. Stainless steel has a lot of dents, and that's called plastic deformation. That deformation is because of little slip behaviors that happen along these planes. So along this line, for instance, when the ball bounces, it can make a little nudge that moves the atoms next to each other. But in the amorphous material, there's really no planes for that to slip on. So we actually end up with what we call atomic gridlock. Nothing can really move around. So instead of using energy to make slip, all the energy comes back to the ball. That's why we get so much bouncing with the amorphous metal. Let's try the experiment again, and this time we can count how many times the amorphous metal bounces back versus the stainless steel. Are you ready? 1, 2, 3. That's a huge number of bounces for the amorphous metal, and only just a few for the stainless steel. Why do you think it stops at all? If most of the energy is coming back to the ball because we don't get this plastic deformation behavior, what else is going on? Do you have any ideas? You're right. Well, sometimes you saw that the ball actually hits the side of the tube, and that actually slows it down a little bit. What else? Well, you're right. There's some air that it has to go through every time, and that is a little bit of friction. The other thing is we heard noise, right? And so that acoustic energy is taking up some of the energy of every bounce because it's making noise every time it bounces. There's a couple of applications for this. So this plate right here on the driver is actually made of amorphous metal. And why do you think that would be helpful? Well, it turns out you're right. You can get a really long drive and get that golf ball to go very, very far if you hit it with amorphous metal versus just regular stainless steel. You might be surprised at how many ways you can take advantage of this atomic trampoline behavior. It turns out that amorphous metals have been used in industrial coatings to prevent wear. They've been used in medical instruments to make very sharp surgical knives. The military uses amorphous metal to make armor-piercing ammunition. And NASA has used amorphous metal in the Genesis spacecraft in order to collect particles in space.